In this video, I'm going to discuss the use of scatterplots and correlation coefficients to study the relationship between two variables. One of the main objectives of statistical analysis is to study relationships among different types of variables. For instance, I might be interested in studying the relationship between the number of children a person has and level of support for funding for public schools. I might suspect that people who have more children will tend to exhibit greater support for increased funding than people with fewer children. I might wish to explore the possibility using a scatterplot and/or computing and testing a correlation coefficient. On the other hand, I might be interested in determining whether a relationship exists between a person's level of fear of being a victim of violent crime and support for decreasing police presence in his or her neighborhood. I might suspect that people who exhibit greater fear of being a victim will score lower as opposed to higher in their support for decreasing police presence in their neighborhood. Again, I could explore this possibility using a scatterplot and/or by computing and testing a correlation coefficient. Scatterplots provide a graphical approach to look at the relationship between two variables, and these are generally variables that are scaled at an interval or ratio level of measurement. Correlation analysis yields a numerical index in the form of a correlation coefficient, and this index is the type of relationship that exists between two variables. In other words, it pretty well summarizes the information that's contained in a scatterplot if the relationship between two variables is linear. So in other words, we can talk about a relationship as being positive or negative or no relationship, and we can test that relationship with correlation analysis. Whereas the scatterplot is generally more of a visual approach to examining a relationship. In this video, we're going to talk about two types of correlation coefficients. The first is Pearson's correlation coefficient, which is denoted by R, and it indexes the relationship between two variables that are treated as continuous. And generally, these variables are scaled at an interval or ratio level of measurement. Kendall's tau, B, indexes the relationship between two ordered variables, or basically two variables that are ordinal in scale. So the first thing that we're going to do is start by discussing scatterplots, and then we'll move into talking about Pearson's correlation, and then we'll talk about Kendall's tau. So what is a scatterplot? Well, basically a scatterplot involves plotting out the coordinates on two variables for a set of cases in 2D space. So basically we have an XY coordinate plane, and essentially for each case or each observation in the data set there are two variables. So in this illustration right here, we're going to create a scatter plot where we have two variables. Variable X is the number of parking tickets in the past 6 months. Variable Y is the number of speeding tickets in the past 6 months. So imagine that I've gone out and asked 6 individuals, how many parking tickets did you have and how many speeding tickets did you have? So the number of parking tickets would be variable X, and it's denoted down here on the X-axis. The number of speeding tickets is denoted with variable Y, and that's being represented along the Y-axis. So we can see that person 1 in the data set indicated that he or she had 2 parking tickets and 3 speeding tickets. So we would plot that person's coordinate on our plane by moving over 2 on our X variable, so 1, 2, and then going up 3 on the Y variable. So we're starting at 0 here, just go 1, 2, and 3. And so this is that person's coordinate on the XY coordinate plane. You can see the coordinate printed out here. Usually in scatterplots you don't see the actual coordinate given, you just see the plot of data points. But in this system right here, the 2 is representing the value on X, the 3 is representing the value on Y. Now let's look at person 2. That person had a value of 1 on variable X and a value of 0 on variable Y. So that person's coordinate would fall right here. Now let's look at person 3, and you can see that person had a value of 0 on X and a value of 2 on Y. Person 4 had a value of 4 on X, so there's 4 on X, and 3 on Y, so that person's coordinate is here. Person 5 had a value of 3 on X and a value of 5 on Y, and then person 6 had a value of 1 on X and, 1 on X and a value of 2 on Y. So you can see that there's a trend in this data set. And basically, you can see that with higher scores on X, those scores are associated with higher scores on Y. So and lower scores on X are associated with lower scores on Y. So what that means in this particular illustration is that people who tended to score higher or indicate that they had more speeding tickets also tended to indicate that they had more speeding tickets. Whereas people who indicated that they had fewer parking tickets also indicated that they had fewer speeding tickets. So you can see that there is a trend, and this is basically what is referred to as a positive relationship between our two variables, X and Y, or in this case, basically number of parking tickets and number of speeding tickets. Here's another example. In this case, this is plotting out a negative relationship between two variables. So in this case, let's say we've asked 6 individuals to indicate the number of speeding tickets they've had over the past 6 months, and using a scale, say maybe between 1 and 5, their level of support for increasing speeding fines for speeders. So as you can see, for person 1, that person has a value of 0 on X and a value of 4 on Y. So that's this person's coordinate. Person 2 has a value of 3 on X and a value of 2 on Y. Person 3 has a value of 2 on X and 1 on Y. Person 4 has basically a value of 2 on X and a value of 3 on Y. That's this person's coordinate here. So you can see that we have a negative trend, and basically with a negative trend, higher scores on X are associated with lower scores on Y, and lower scores on X are associated with higher scores on Y. So in other words, in this illustration, people who tended to have more speeding tickets also tended to indicate lower support for increased fines, whereas people who had fewer speeding tickets indicated greater support for increased fines. So these are some general illustrations of trends that you might find in your data in terms of being positive, negative, or no relationship. So basically, right here you can see this is a positive relationship. Higher scores on X are associated with higher scores on Y. Lower scores on X are associated with lower scores on Y. With the negative relationship, higher scores on X are associated with lower scores on Y. Lower scores on X are associated with higher scores on Y. And then with no relationship, as scores increase on X, there's no systematic tendency to exhibit greater or lesser values on Y. Also note that the stronger the relationship that exists between two variables, the more those data points that you see right here start to fall on the line itself. Whereas the weaker the relationship, the more horizontal the line becomes, and the data points exhibit more variation around this line. So you can see right here, this is no relationship. This means, and you can see it's a perfectly horizontal fit line. And basically, if I was plotting out my data points, they would be randomly dispersed around this line right here. Whereas if I have a perfect positive relationship, the data points would actually line up on the line. As you can see right here, our perfect negative relationship, the same would occur. So how can I obtain a scatter plot in SPSS of the relationship between the number of parking tickets and the number of speeding tickets? Basically our first example. To do this, we would have, first of all, we would need to have in SPSS 2 variables. The first variable is number of parking tickets. The second one is the number of speeding tickets. So we have persons 1 through 6 and the values on our X variable and Y variable for each person. So the next thing that we would do is, after we put our data in for our variables, we would go to Graphs, Legacy Dialogs, and then down to Scatter Dot. Then we would click on Simple Scatter, and this box right here will open up. And I'm going to move number of parking tickets over to the X-axis, as you can see right here, and number of speeding tickets to the Y-axis, as you can see right here. So when I click the OK button, this graph pops up. So this, and so as you can see, this is pretty much the same thing that we had earlier when we were doing this manually. And so if I want to get a trend line to look at you know, the relationship a little bit more clearly, we can certainly do that. I can double click on this particular box in the output, and then this little menu option will highlight, and where if you put your cursor over this little button right here, it'll say add fit line at total. I just clicked on this and this line appeared, so it gives me a straight line that's fitted to the data. I can click out just by clicking the X box right here, and there you go. So you can see that we have a pretty strong linear trend, positive linear trend between number of parking tickets and number of speeding tickets. Now let's look at generating a scatter plot, looking at the relationship between number of speeding tickets and support for increased fines. So in this case, I'm just putting number of speeding tickets on the x-axis, increased fines on the y. I'll be perfectly honest, you know, the X and Y designations are largely arbitrary, so there's nothing special, but in this particular case. But this is just how I've laid it out. I'm just laying out number of speeding tickets as X, increased fines for Y. Clicked on OK, and so generating the trend line in the same fashion I did earlier, you can see that we have basically a negative relationship between our two variables. Now, the scatter plot, as you can see, provides a visual depiction of the relationship between two variables, but it's not particularly succinct in terms of communicating about that relationship. So what we can do is we can generate a correlation coefficient to denote the relationship, and a correlation coefficient gives us an idea about two things: the direction of the relationship between two variables and the magnitude of the relationship. So if I'm interested in studying the relationship between two variables that are scaled at an interval or ratio level of measurement, then I'm going to be utilizing Pearson's correlation coefficient, also known as Pearson's R. And Pearson's R values range on a scale between -1 and +1. And a value of 0 indicates no relationship between the two variables. A value of -1 indicates a perfect negative relationship, meaning that there's a one-to-one relationship. As you know, for every 1 unit increase on X, there's a decrease of 1 unit on Y. And these are actually in standardized units, but nevertheless, it's a perfect relationship. In terms of a positive one, it's a perfect positive relationship between the two variables. You can see in between the negative relationship that you see right here for an R value equal to -0.5, it's a little flatter than it was right here, but not quite as flat as we would see with no relationship. So this is denoting a weaker relationship than what we would have if we had an R value equal to -1. But certainly this is a stronger relationship than an R value equal to 0. The same would apply on the positive side. So as we move closer to 0, from -1 to 0, the negative relationship becomes weaker and weaker, and the line actually becomes increasingly horizontal. The same general principle is true if we move from 1 to 0 in the opposite direction. The positive relationship depicted by the line becomes more and more horizontal. So as you can see, the scale that we're using, basically we have positive correlations and negative correlations. The positive correlations indicate a positive relationship between two variables. Negative correlations indicate a negative relationship. And as we move from 0 to +1 or -1, that is indicating the magnitude or the strength of the relationship. And so as we move closer to 1 or -1, the relationship between the two variables is becoming increasingly strong. So this is what's being denoted basically right here. So as you can see, as we move towards -1 or +1, that's denoting a stronger relationship between two variables. As we move closer to 0, that's depicting a weaker relationship. Now, correlation coefficients are often tested for statistical significance, and basically what this means is that the assumption by default with the null hypothesis is that the correlation between two values in the population looks like this, meaning that there's no relationship between the two variables. And so what we can do is, generally researchers don't believe that the null is true when they're testing the hypothesis, but the null is sort of a straw man that you compare your data against. And researchers will generally adopt one of three possible alternative or research hypotheses concerning the population correlation. One hypothesis is that there's a positive relationship in the population, and another possibility is that there's a negative relationship. And in both of those cases, that's B and C right here, those are what are called directional hypotheses. In other words, you are specifying that the population correlation is either greater than 0 or less than 0. Another possibility is that there is just simply a significant relationship, meaning that the population correlation is not 0. And this is actually referred to as a non-directional hypothesis. So we have two general classes of hypotheses. There's directional and non-directional hypotheses. Non-directional hypotheses are concerned just with testing whether the correlation in the population is not 0. A directional hypothesis is concerned with testing whether the correlation is greater than 0 or less than 0. Possibility A requires what's called a two-tailed significance test of the null hypothesis. Possibility B or C requires a one-tailed test. So this is an example of what we're talking about. That basically the null hypothesis is always going to be that the population correlation is equal to 0. Or generally is that the population correlation between your two variables is equal to 0. And this is actually referred to as a sampling distribution. This is the T or the sampling distribution of T. And what we're doing is we're looking to see where our data falls in relation to the null hypothesis. So if the correlation that we observe in our that's computed from our data puts us in the upper tail of this distribution or the lower tail of this distribution, if we're assuming that the population correlation is not equal to 0, which is our research hypothesis, then we would conclude that that we can reject the null hypothesis, and we would conclude or infer that the population correlation is not equal to 0. If the correlation we observe in our sample data puts us in this region right here, then we essentially will infer that that the population correlation is equal to 0. In other words, we would maintain the null hypothesis. So in other words, what we're doing with this distribution right here is we're taking into account the role of sampling error with respect to the correlation that we compute from our data. And if the correlation that we compute from our data puts us in this tail or this tail, then we're going to infer that the difference between what we observe in our sample data and the null hypothesis is unlikely to be due to sampling error and more likely to be due to a real difference. If the correlation that we observe in our sample puts us in this region, then we will infer that the difference between our correlation value and the null is reflecting sampling error, in which case we would assume that the null hypothesis is equal to 0. Now, let's say our research hypothesis is that the population correlation is greater than 0. In this case, we would be testing in the upper tail of this T distribution right here. And basically, we would reject the null hypothesis if the correlation that we observe in our sample data puts us up here. If the correlation we observe in our sample data puts us anywhere from this point on down, then we would maintain the null hypothesis. The same general logic would apply if our research hypothesis was that the population correlation is less than 0. In this case, if our sample correlation puts us out in this region, we would reject the null hypothesis and conclude that our population correlation is less than 0. If our sample correlation puts us in this region right here, we would maintain the null hypothesis and infer that the true population correlation is equal to 0. So basically, this is the research hypothesis for where we assume that the population correlation is not equal to 0. This is basically a non-directional hypothesis, and in this case we're using a two-tailed test of that hypothesis. In this case, we have a directional hypothesis. In this case as well, we have directional hypotheses, and a directional hypothesis would imply a one-tailed test. You could certainly get more details on the logic of this process by consulting a lot of stat textbooks, but this is just kind of to give you a general idea of the difference between directional and non-directional hypotheses and one- and two-tailed tests for the significance of a correlation coefficient. And this is what's necessary in order to kind of understand what's going on when you're running correlation analysis using a program such as SPSS. Also, in addition to testing for statistical significance, researchers will also try to describe the magnitude or the size of the relationship between two variables. Jacob Cohen in 1988 suggested the following conventions for judging the magnitude of a correlation. And he was mainly using this as it pertains to the social and behavioral sciences. So basically he suggested correlation values and correlation coefficients in absolute value around 0.10 would be considered a small relationship. So if I had a value, let's say around 0.10 or negative 0.10, in both of those cases, the difference between that value of 0.10 and negative 0.10 and 0 is the same distance between those values and 0. And so that would suggest in either of those cases you would have a small relationship between the two variables. A medium relationship would be indexed by a correlation in absolute value of 0.30 or around 0.30. So in this case, the distance between 0.30 and 0 and negative 0.30 and 0 is the same distance on either side of the scale, and so in this case that would suggest a medium relationship. And then values of 0.5 or negative 0.5, those would be considered large. So values at that level or greater would be considered large. So how would we run Pearson's R in SPSS? Well, here we have data on number of parking tickets and number of speeding tickets for our 6 individuals. And let's say we want to compute Pearson's R to examine the relationship, and let's say we hypothesize, our research hypothesis, that the relationship between number of parking tickets and number of speeding tickets is non-zero in the population. So this is basically a non-directional hypothesis and would imply a two-tailed test. We adopt what's called an alpha criterion that's generally set at 0.05. That's a convention. And we compare the p-value that is computed from the data against that value. And if the p-value that is printed out in your output is less than or equal to 0.05, then we would infer that the research hypothesis is the correct state of affairs, and the null hypothesis is likely to be the incorrect state of affairs. So this box will come up after we basically go to Analyze, Correlate, Bivariate. We move our two variables over to this box. Pearson's is set by default, and we can see where it says Test of Significance, we're going to go with two-tailed. So when we click on OK, this output will come up. You can see in the primary diagonal you've got ones, and on the off diagonal you've got the same values. So you really only need to look, at one of these two cells right here. So we can see that Pearson's correlation coefficient is 0.62. So if we use Cohen standards to judge the magnitude of the relationship, we would say that the relationship between number of speeding tickets and number of parking tickets is large. So here's the p-value for our analysis, and we are comparing that against what's called the alpha level, and alpha is our tolerance for committing a type 1 error. In other words, a type 1 error just basically refers to essentially rejecting the null hypothesis when it is in fact true. So in other words, we would be, if we were committing a type 1 error, we would basically be saying that there's a relationship in the population when in fact there's not. So that's our threshold for rejecting the null and feeling more comfortable about saying that yes, there's a relationship as opposed to no relationship. So if our p-value is less than or equal to 0.05, that's our alpha level, then we reject the null hypothesis and infer that the true population correlation between the two variables is not 0. So we can see, though, that the p-value that's printed out right here is 0.189. That's clearly greater than 0.05. So based on this, we would not reject the null hypothesis, and we would infer that the null is actually true, that within the population, the relationship between number of parking tickets and number of speeding tickets is equal to 0. Now let's say we had hypothesized a positive relationship between the two variables. In this case, this would be a directional hypothesis, and it would imply that we use a one-tailed test for that hypothesis. So we would run the data analysis in exactly the same way, but in this case we would click on one-tailed as opposed to two-tailed. You can see now it says SIG, one-tailed. Previously it said SIG, two-tailed. So in this case right here, this is the p-value for a one-tailed test. And again, our data is exactly the same, so the Pearson's correlation is exactly the same. The only difference is the p-value. And you can see that the direction of the relationship is as we expected. We had hypothesized a positive relationship, so the correlation is consistent with that hypothesis, but we also see that our p-value is greater than 0.05, so we cannot reject the null. We basically have to maintain the null, and we would still infer that the true population correlation is equal to 0. Now, let's say that our correlation had been negative. In that case, we wouldn't even need to borrow looking at we wouldn't need to consider looking at the p-value because the relationship would be contrary to our original directional hypothesis. That's not the case in this illustration right here, but that is something to consider. Sometimes you can have correlation values that are contrary to a directional hypothesis, in which case there's no point in going any further. We would say that we would infer that the true population correlation is 0. So let's say we're hypothesizing a negative relationship between number of speeding tickets and support for increased fines. In this case, again, we're running Pearson's correlation, but because we're specifying a negative relationship, then we have a directional hypothesis which would imply a one-tailed test. So we click on that and click on OK, and so here's the negative relationship. Pearson's R is negative 0.801. So using Cohen standards, again, this would be a strong negative relationship between the two variables. The p-value for the one-tailed test is 0.028 and is clearly less than alpha set at 0.05. So in this case, we would reject the null hypothesis and infer that the true population correlation is significantly less than 0. Now, Kendall's tau is a different type of correlation coefficient that can be computed. It's computed when you have two variables that are scaled at an ordinal level of measurement. That is, the values on the variables represent ranks. This index is interpreted largely in the same fashion as Pearson's correlation coefficient, with values ranging from -1 to +1. Positive values indicate a positive association between the variables, and negative values indicate a negative association. A value of 0 indicates no relationship. So here's some data. In this case, we've got two variables, interest in politics and intention to vote. So in this case right here, we have for interest in politics, it's got values of 1 equaling none, 2 equaling some, and 3 a lot. So these are not very precise values for this variable, and it's certainly not approximating any type of continuous variable. So these are more akin to ranks in this system. Intention to vote is also largely the same scaling. We've got 1 being none, 2 equaling some, and 3 equaling a great deal. So these two variables we're going to treat as being ordinal in scale, and so we're going to test a non-directional hypothesis that the population correlation will be non-zero, and we're going to set alpha at 0.05. So I go to Analyze, Correlate, Bivariate. I move my two variables over here, and instead of clicking on Pearson's, now I'm going to click on Kendall's Tau B. Because this was a non-directional hypothesis, I'm going to have a two-tailed test. Click on OK, and so here is my output. So you can see that the correlation between interest in politics and intention to vote is 0.424. So that's a fairly moderate relationship between the two variables, kind of going back and thinking about Cohen. But the p-value is 0.154, which is definitely greater than 0.05 for our alpha level. So in this case, we would infer then that there is not a significant relationship between the two variables in the population. In other words, we're not going to infer that the correlation is different from 0 in the population. A few other examples of scatter plots and correlation analyses, and I do want to note that all the data in this PowerPoint are completely fabricated just for the purposes of the illustration. So these aren't real data, just kind of so you know. So here's just a data set that I generated, and you can easily, from this PowerPoint right here, you can easily put this data in and run these analyses. I've got, this is a pretty lame example, but it was designed to illustrate a lack of relationship between two variables. I've got how much do you like cheese and how much do you enjoy statistics. So I generated this data so that there is 0 correlation between the two variables, and I generated a scatter plot, and you can see here's the line of best fit. It's horizontal, and the plot of data points around this line are random. So there's no systematic tendency, as you can see, as scores increase on X. There's no systematic tendency to score higher or lower on Y. Here's an example of the relationship between how much a person likes algebra and how much they like geometry. In this case, I generated this data so that it has a correlation of 0.34. And as you can see, this is a fairly moderate positive relationship. Here's the scatter plot, and you can see the data points still fairly dispersed around this line of best fit, but you can definitely see a trend, a positive trend in the data. The p-value is not indicating statistical significance. So if I was actually testing this correlation, I would not be inclined to reject the null hypothesis. I would be inclined to infer that the true population correlation is more likely to be 0 than non-zero. So in this case, I generated another set of data where it has a much stronger relationship. Actually, this is quantitative ability and fear of using quantitative research methods. So basically, I generated this so that there would be a strong negative relationship. The correlation is negative 0.82, which is very strong using Cohen standards. And as you can see, the line of best fit, there's more angle to it, obviously, and you can see that the data points are less randomly dispersed around this line than what you saw right here. You can see right here there's a lot more spread of the data points as opposed to here where it almost looks more like an oval. And the stronger the relationship between the two variables, the more these data points would fall on the line. Here's just another example. This is generating a relationship between level of higher education and support for reduced funding of higher education. So in this case, I'm treating these two variables as being ordinal, and I generated the relationship between them using Kendall's tau B. And so the correlation between them is negative 0.617. And you can see that the p-value is actually less than 0.05. So, if I was just testing whether there's a significant relationship between the two variables, I would be inclined to infer that I could reject the null hypothesis and infer that the relationship between the two variables in the population is not equal to 0.